brief intro to Nixon. He's been at Stat Central for a year and he's going to take over as seminar coordinator. So you're going to see a lot more of him in our seminar intros. A brief intro to Stat Central for those who are a bit new to who we are and what we do. So we're a stats consulting service. We service the whole university, so all HDR students and staff are eligible to come and see us for a consultation. And if you're a partner school, you might be eligible for some extra assistance as well. So yeah, we can help you with study design, analysis plan, all sorts of stuff. And we run lots of courses and love to see you at our courses later in the year. I'll let Nixon do his seminar.
Thank you, Eve. All right. Let me stop this. Sorry.
You want me to set it up?
Okay. Hope everyone can hear me. Okay. Hello, everyone. So today I'm going to give basically just a brief intro, a gentle introduction to some concepts in causal inference. So let's get started. Okay, so just getting right into it. What is causal inference? Actually, could I zoom in this? Okay, so I guess if you're learning about something, probably your first question might be, well, what is that thing? So here in this slide, I have gathered 3 quotes from various corners of the internet that try to define what causal inference means to them. So let's slowly, I guess, read through this just quickly. So the first one here, we have the process of determining the independent actual effect of a particular phenomenon that is a component of a larger system. The process of determining that a cause led to an effect, or understanding under which circumstances correlation does actually imply causation. So these 3 points, I'm not sure how it feels to you guys listening to this talk, but to me, they're kind of fairly vague definitions. It could kind of mean, in some sense, whatever you want. And I guess a consequence of this kind of vague definition is that causal inference as a field of study in statistics is actually quite a large field. So in this next slide, I have I've listed, like, I guess, some topics within causal inference that you may or may not have heard of. I won't be talking about all of them. So in particular, I'll be talking about these 3 at the top, highlighted in blue. So G-computation, inverse probability of treatment weighting, and targeted maximum likelihood estimation. So in the past, we've also had another consultant, Nick Olson, who talked much more in depth about inverse probability of treatment weighting. So I won't be going as in depth into that, but I'll be kind of more just talking about it more generally and maybe more basically, but also about other methods as well. So these 3 methods highlighted in blue, they were created to deal with the problem of when you have measured confounding and also in the setting of binary treatments. So, I mean, these other methods that I've listed down here, which you may or may not have heard of, they'll often be dealing with different problems. So, for example, instrumental variables, they can actually deal with unmeasured confounding. And then there's also stuff like dose response analysis, which is when you don't actually have binary treatments. And so, well, what I've listed on this slide is really just a small component in the whole causal inference field. So just keep that in mind. But even with these 3 points that I'm going to be talking about today, I think you can already it's probably enough information for one seminar. So let me give the most generic example possible of a type of problem that you might be thinking about. If you have kind of your own research question in mind, that is perfectly fine. You should probably keep that in mind as well. So this example is kind of, I guess, meant to give you just a simple example in case you don't have anything in mind of what a binary treatment looks like and what measured confounding might look like in a data set. So this example is just maybe you have a treatment that you're looking at and you want to see its effect on PET. So I have this notation y and x, which I'll be using a little bit throughout the talk. Hopefully not too much to bore you, but basically you have this pain score y, and you have a treatment which either you don't have treatment or you have treatment, which I'll denote A here. So that's either going to be 0 or 1. And then you also might have some confounders. In this case, I'm just going to call it, I denoted X, and I'm going to call it so something like the severity of the disease, for example. You could have more than one confounder, but in this talk, I'll just be focusing on this one confounder. So you might be asking the question, does my treatment cause the pain to decrease? Very normal question to might want to know the answer to. So a thing here is that in this example is that it might actually be more ethical to provide treatment to those with more severe disease, and that can actually lead. So that would be, I guess, a practical example of why you might not be able to actually do an RCT in practice. So I'll be talking about randomized controlled trials very soon as well. But just keep it in mind that sometimes it might not be ethical to just randomize your treatments to different patients, even though statistically that might be the ideal thing to do. Okay, so next I want to talk a little bit, maybe just spend a minute or two talking about philosophy. So causality is philosophical. And what do I mean by that? So I'm not going to talk about this too much, but there's a few things to think about when you're thinking about causality, not just from a statistical standpoint, but also, I guess, from a standpoint of the theory of knowledge or how you maybe interpret the world. So, for example, if, let's say I gave a treatment to someone and it caused them, maybe there's a side effect and then maybe they die of blood loss. Okay, not a good result. But if you did something like that, and then you might be tempted to say, well, my treatment caused this death, for example. But if you think about it a little bit more, like in between, there's this step of blood loss in between which caused the death. So if you were actually able to maybe have another different medicine that stopped that blood loss, then actually your treatment wouldn't have caused the death. So would you really say that it was your treatment that caused this death, or would you say that it was actually the blood loss that actually caused the death? So that's something to think about. Another thing you might want to think about is the nature of the universe. So I did say this, I will be spending 2 minutes talking about this. So if you believe in determinism, then I guess from the very beginning of the birth of the world, however you want to interpret that, then every single, I guess, thing was already determined from the beginning of the world. Then can anything actually even be called causal? Does something actually cause something? Or was it all just predetermined? That's also something for you to think about while you're lying in bed. So a third thing here is stochasticity. So if and this is, I guess, maybe a bit more practical to think about, but if your treatment maybe only increases the probability that someone maybe has decreased pain or whatever, maybe it will increase or decrease the probability by like 10% or whatever. Would you call that causal when it's just affecting the probabilities a little bit? Or to you would you only define causal as if something for certain causes something else? Only then would you perhaps call it causal? So again, that's something for you to think about, and I cannot answer. But so, well, that was the slide. But in this talk, I won't really be talking about those things, even though I just did. So what I really want to talk about in this course is how we as statisticians, I mean, not in this course, in this seminar, how we as statisticians might think about causality. And here we actually have a, I think, decently well-defined way of talking about causality. And it's called the counterfactual framework, or the potential outcomes framework, also known as the Rubin's causal model. So again, a little bit of notation here. So basically, well, for some observation I, the main point is that, at least in this setting, when you have binary treatments, is that they are kind of, each time you do an experiment, so each time you either give or not give someone a treatment, you imagine, I guess, that there are two possible potential outcomes. So whenever you have, let's say, a patient, then you would, I guess, think about their outcome, yi0, what would happen if you didn't give them the treatment, and then versus the outcome yi1, which is what would happen if you did give them a treatment. So the if you're familiar with like simulations and if you're statistics, then basically in the simulation you would kind of generate both the potential outcomes yi0 and yi1 when you're kind of trying to evaluate whatever methods. But I'll be talking about that a little bit later as well. So basically, yeah, so for each time you do the experiment, you have a patient, there's, I guess, their pain score, for example, if you didn't give them the treatment, and then their pain score if you did give them the treatment. And then basically any comparison between these two potential outcomes is by definition causal. So, for example, a common way or a common choice of comparing the potential outcomes is to look at the expected value of your expected, let's say, pain score here under the treatment minus the potential outcome if you didn't have the treatment. And you will want to look at the expected value of that. So that would be probably the most common that I've seen way that people like to examine causal effects. That's to look at the average treatment effect. But there's also some other, many other choices, such as the expected ratio. So this quantity here, or you can look at medium of difference. I guess the local average treatment effect is something that is somewhat commonly looked at as well. Yeah, but anyway, the average treatment effect isn't the only thing that you can look at if your goal is to do causal inference. So yeah, any comparison between the potential outcomes is causal. Okay, so that's all well and good. So that was the counterfactual or the potential outcomes framework. But I guess the problem is that we only actually observe, in reality, you can only either give someone a treatment or not give someone a treatment. You can't kind of do both and look at the result if you did both. And so the unobserved one is called the counterfactual. And here is where the fundamental problem of causal inference lies, and that is that you cannot observe both. If you could observe both, then you can kind of just directly compare the potential outcomes and then make your conclusions from that. Okay, but we can't. So the way we kind of solve this is that you'd want basically multiple observations that are very similar. So for example, maybe if you could like clone a person and make every like all the variables the same, control everything, then you can maybe get pretty close to be able to observe like different potential outcomes. But again, we can't do that in reality. So what we do instead is we try to find multiple very similar observations and then try to do some adjustments from that. So before I talk about some methods to actually kind of go about doing that, I want to talk about the randomized control trial. So for those who maybe aren't familiar with this, it's basically if you have a treatment, then for each maybe person in your experiment, you either basically you randomize whether or not they get the treatment. And this is kind of considered a gold standard for causal inference. Now, you might have heard that thrown around, but there's a few reasons, even statistically, why that is the case. So, for example, it actually guarantees that your treatment doesn't get confounded with other variables. It also guarantees that the probability of getting the treatment is strictly between 0 and 1 for your samples. And so kind of with these two guarantees, you can actually show that, well, you can show many things, but I guess an important thing you can show, for example, is that you can prove that the difference in the sample means between the treatment and control group is actually an unbiased estimator of the average treatment effect. And so this point here, the fact that you can prove this, it kind of justifies. So you might have heard along somewhere in your studies that you can kind of just assume that you can kind of fit this linear model and then just assume that your epsilon is actually normal 0 sigma squared if you've done a randomized control trial. And I guess one way that you can justify that is because if you kind of just fit this normal model, assuming the errors are independent and everything, then what you end up with is you'll have basically the difference in your means between the treatment and control group as your estimator for the average treatment effect. And that's fine in a randomized control trial because you can prove that it's always an unbiased estimator of the true average treatment effect. So that's a little tangent there. So next, I guess, so in a randomized control trial, you can always kind of just compare the sample means, but in observational data, that turns out to no longer be true. So with observational data, if you can't randomize your treatments, then it turns out that, well, basically your difference in sample means probably won't be an unbiased estimator of the average treatment effect. And in particular, there will likely be confounding. But the good news is that we can actually adjust for the confounding if it's measured. So what I mean by measured, I mean basically it's you can actually observe those variables. So for example, in my example, it would be the disease severity might be correlated with whether or not someone gets a treatment, because maybe you want to give the ones with more severe disease treatment. So, okay. So next I'm going to be talking about those three methods that I listed in my little blurb that actually adjusts for the measured confounding, in this case of binary treatments. So before I go into those three methods, they actually all have a bunch of assumptions that need to be met before they can actually be considered valid or unbiased estimates of your of your average treatment effect, which is what my main aim is to be talking about today. So all these methods I'm going to be talking about, they aim to get that average treatment effect. And they all assume that there's no unmeasured confounding. Hopefully that's self-explanatory. They also all assume positivity. So what that means is every single sample has a probability that is strictly between 0 and 1 of receiving the treatment. There's also this stable unit treatment value assumption at the end, which basically means your different samples don't interfere with each other. It's actually a bit less strong than that, but you can think of it as, yeah, your samples don't really interfere with each other. And lastly, there's actually this consistency assumption. Y is equal to YA. So this one's actually, so what that means is that for example, the pain score that you observe is actually the pain score that you observe when you give a sample the treatment. Okay, so that kind of sounds like a tautology, right? So it sounds like it should kind of naturally just be true by default. And I guess in some cases it is, but it's also quite this assumption there is actually quite sinister, because there's a way that there's quite a few ways that you might not actually observe your underlying potential outcome when you give the treatment. So for example, there might be if you're looking at something like length of stay or something, there might be some right censoring. Your patient might die before you can observe their full length of stay. Then in that case, the length of stay that you observe won't actually necessarily be the length of stay, the actual length of stay, given that they were given or not given the treatment, if that length of stay was actually observed. So yeah, that's one way this consistency assumption can go wrong. So with the censoring, some other ways that it can go wrong might be, for example, if you didn't blind your experiment, if you didn't double blind your experiment, then the reported pain score might not actually be the underlying pain score that a patient is experiencing. So there's kind of actually many ways this consistency assumption can go wrong. So that's something all of these assumptions you really need to think about for your own data before you can proceed to apply these methods that I'm going to be talking about. Okay, so with that out of the way, let's talk about those three methods that I said I would talk about. So the first here we have G-computation. And basically the steps are to just model your outcome or response as a function of your treatment and confounder. So I guess let's just stick with our example. So you could model the pain score as a function of whether or not the patient had a treatment and also their disease severity. And this can be, so for example, it could just be a linear regression. But I guess part of the power of these approaches is that you don't have to stick with these parametric or these typical assumptions that you might make about the structure of the model, of the true model. Instead, you could also, for example, here go with like various machine learning methods, like I don't know, your regression trees or whatever you like, really. And then, so that's the first step. You just model your outcomes as a function of your covariates or your independent variables. And then the second step is for each sample that you have, you want to estimate the expected value, the mean response, given that the treatment was given to this particular sample. And you also want to estimate or predict, if you like, the mean outcome, given that the treatment was not given to this particular sample. So for each sample, you want to predict what the outcome would have been if they had the treatment, and also what the outcome would have been if they didn't have the treatment. And then basically you just take the mean of the difference of those two over all of your samples. So this is, I guess, quite intuitive, because you basically just you've kind of converted the problem into a prediction problem, and you're just trying to predict your, I guess, your mean if you had the treatment versus if you didn't have the treatment. And so by way of doing that, you're also trying to, I guess, predict basically the mean of your potential outcomes as well. And so if you do that, that will actually give you an unbiased estimate of your average treatment effect if your outcome model is correct. So that can be a big if. And so maybe, for example, if you're not too confident in what the outcome model might look like, there's another thing you can try, which is called the inverse probability of treatment weighting. Now, again, this Nick has talked about this in a previous seminar in much more detail, but I'll kind of just simply go over it here as well. So for the inverse probability of treatment weighting, what you want to do is you want to model the probability of receiving a treatment, the probability that AI is equal to 1 as a function of your covariates or your independent variables. So in this case, the disease severity. So if you kind of compare here, my first step here is to model the probability of receiving treatment, whereas in this G-computation method, my first step is to actually model the responses as a function of my covariates. And the second step here is you basically want to upweight each observed outcome by its probability of receiving or not receiving the treatment. And what this kind of does is, in a sense, it gives you a pseudo, you can think of it as kind of giving you a pseudo RCT, if you like, because it balances basically the covariates, or tries to balance the covariates between the groups. And so after you upweight each outcome, you can just sum all of the upweighted outcomes separately for the treatment and the control group, and then you can subtract the sum for those two groups, and then finally divide by the sample size. And that will give you an unbiased estimate for the average treatment effect if your treatment model, that is this model for the probability of receiving the treatment, is actually correct. Okay, so these two methods, so this one here, your outcome model needs to be correct. And this one here, your treatment model has to be correct. That, I guess, in a sense, naturally begs the question of could you possibly combine kind of the good points of both of these methods into a method that maybe only one of these models needs to be correct. And yeah, that's exactly what I've been talking about. So there's this method called the targeted maximum likelihood estimation. So basically this, I guess this method is considered a kind of gold standard in causal inference these days, alongside some other ones. But in particular, like it's considered better than the G-computation and the inverse probability of treatment weighting because it has this so-called double robust property. So these steps are a bit complicated, so I'll kind of just run over them briefly. But basically, it tries to combine the outcome model that you have, as well as a treatment model, probability of treatment model, and then by combining it in a kind of, I guess, really clever way, what it achieves is that basically only your outcome or treatment model needs to be correct. So you can actually afford to get one of those wrong, and your estimator for the average treatment effect is still going to be unbiased. So I guess let's briefly talk about these steps. They are a little bit complicated, but the main steps are kind of just, I guess, a bit of a combination of the previous two. So in the first step, you want to model your expected value of y, so your mean outcome or your mean response, given that the sample was given a treatment or not. So this is basically the same step as the G-computation step. And then in the second step, you model the probability of it getting treatment, depending on the confounders or the independent variables that you have. So this is kind of the same step as in here, the inverse probability of treatment weighting. And then, so here it gets a little bit, I guess, technical. So a bunch of smart people, they got together and they came up with I guess these number of steps where if you do them, then you're good. But basically, you want to create some so-called clever covariates, which is just so it's basically just the inverse weights that you have. So it's the inverse probability weights. But I guess only like I guess the observed inverse probability weights. So if a sample did receive the treatment, then you want this then you want your clever covariate GI to be 1 to be 1 over the probability that they did receive the treatment. And then if they didn't receive the treatment, then instead you want, then this would be 0. Then the GI would be 0, and then HI, instead you have HI be something non-zero, which is that'd be 1 over the probability of them not receiving treatment. So it might sound a little bit complicated, but when you actually do it, you kind of just follow the steps and then just do it. There's also R packages and various other packages that you can use that will do it for you. But those probably, they won't give you as much control over exactly what models that you might use for the outcome and probability models and probability of treatment models. So steps 4 and 5 is like pretty technical. It's basically just trying to incorporate these clever covariates to improve your predictions of the mean response, basically. And you do a bit of transformation, back transformation, and then finally you just compute the average treatment effect as the difference in your predicted mean response if you got the treatment versus if you didn't get the treatment. Okay, so why would we want to use these methods? So I've kind of talked about this a little bit already, but there's really kind of 2 main points, and it's just these ones on the slide. So it allows one to be agnostic towards the model structure. So if you come back here, you'll see that I didn't really specify any particular way that you have to model your Y or your probability. So what people often do in practice is actually to use, for example, a bunch of machine learning methods, so like boosting, XGBoost, regression trees, classification trees, random forest. Again, whatever you really like, but and the main point is that if you do those things, then you don't have to say, oh, maybe my response is normally distributed with like this linear assumption on all of my other covariates. Or yeah, you also don't have to say, oh, it's like binomial or whatever. You don't have to make any assumption towards your model structure, as long as your machine learning methods or whatever non-parametric methods are actually getting you the your actual mean response given the covariates. So basically, if they're, well, technically your whatever method should be giving you an unbiased predictor or an unbiased estimate of the mean response given whether you got the treatment or not, as well as all the other covariates. So that's kind of number 1. That's probably the most important one. And then the second point is that the methods like TMLE. So there's also some other methods like augmented inverse probability of treatment weighting that is also doubly robust and tries to combine those things. But I'm just going to be talking about TMLE, and TMLE is doubly robust. So you can again afford to get either the outcome or the treatment model just wrong, but you'll still be able to get an unbiased estimator of the average treatment effect. So I guess another point that I didn't mention in the slide is that it kind of, so there's also all the advantages of that come with like kind of converting this problem into like a prediction problem. So for example, if you just wanted to fit a linear model to your Y, but you have like a bunch of covariates, like maybe more than your sample size, then a linear model, you wouldn't really be able to fit that. But like for some more like advanced methods, like some machine learning methods or stuff with regularization, those you can still fit, and then you can still try to get an estimate for your expected value of Y given you're given or not given the treatment. So I guess you could say another advantage would be if you have a lot of covariates, this is something you could do instead of needing to rely on those linear models, for example. Okay, so I'm gonna show just a bit of a simulation. Just to, I guess, try to give an example of what I'm really talking about in those previous things. And again, these slides will be available online. So if you want to have a try yourself, there's code coming up as well. So I guess the simulation study, it's a good. This is kind of the correct way of thinking about the counterfactual framework or the potential outcomes framework. And basically, so here I have my disease severity. I generate that from a Bernoulli 0.75 distribution. So basically 25% of my patients have x is equal to 0, which let's just say that's low severity. And then 75% of my samples have x is equal to 1, which is high severity. And then I also want to generate the treatments. So here I generate from the Bernoulli 0.5. If my disease, if x is equal to 1, that is my disease severity is high, then there's a 50% chance I give these guys the treatment. Whereas if my disease severity is low, so x is equal to 0, then I have a 20% chance of giving the treatment to these guys. And so this line is really like how you see that is the simulation setup is not an RCT, because in an RCT, you would just, well, basically the treatment assignment wouldn't be dependent on the value of your x or any other covariance. And then in this third line here, I'm going to generate basically the pain score. So if this is the potential outcome if a particular sample wasn't given a treatment. So if you weren't given a treatment, then your pain score was generated from a normal 1 plus 3x 100 distribution. And then if you were given the treatment, then your pain score is generated from a normal 5 plus 13x 100 distribution. So if you've been paying attention, you'll find that this is a bit weird because this kind of is actually saying that your treatment is actually increasing the pain scores, which is not good. But this is just made up, so it's all good. So another way of writing this model for y is that you have y is equal to 1 plus 3x plus 4 times 8 plus 10 xa plus epsilon. So basically what this means is that your treatment, if your severity is 0, if you have low severity, then the treatment is going to increase your expected pain score by 4, which is just this number here. But if you have high severity, then the treatment would actually increase your average pain score by 14, which is 4 plus 10. So you never think about that. But basically in this simulation setup, then the true average treatment effect is actually 4 times 0.25 plus 14 times 0.75. So this comes from the fact that those with low severity, their treatment effect is 4, and those with high severity, which makes up 75% of the population, their treatment effect is 14. So that averages out to 11.5. So here, I do want to make a point that something you might want to think about in your own study is, do you really want, is the average treatment effect something you're actually interested in? Is that what you really want? So for example, well, here, this is, you're averaging the treatment effect over your entire population, which is why it's called an average treatment effect. But if you just have this number, 11.5, then you kind of lose out on this information that you have like different subsets of your population that might respond differently to your treatment. So in this case, like the low severity people, their Y is increasing by an average of 4, but for the high severity people, their treatment effect is 14. So you kind of, that information will kind of get lost if you're just going for the ATE, which might still be what you want. So it's for something for you to think about for yourself. Okay, so yeah, I have some code just comparing the different methods in the simulation setup. So I won't like go into too much detail about the code, but I compare a few different methods. I have what happens if I just look at the group means and compare them. I also have what happens if I have the correct inverse probability of treatment weighting method applied. So by correct, I mean my probability model here is actually correct. Whereas I also have this, what happens if you do IPTW wrong? So if your propensity score model or your probability of treatment model is wrong, so here I have this model here just means that I'm assuming that my probability of treatment is the same for all of my samples in the simulation. Well, then that model is wrong, and we have a look at what happens there. And then G-computation, I have G-computation. I also kind of do the same thing. So I look at what happens if I have the correct outcome model, which is just this model here. So with the two, I get the two one-way effects and then this interaction effect as well. And then I have this G-comp wrong, which is look at the wrong when you have the wrong outcome model. So I just didn't include the interaction term there, and we have a look at what happens. And then TMLE, I kind of do a combination of those things. So I look at what happens if you have the outcome model incorrect, if you have the treatment model incorrect, if you have both correct, or if you have both incorrect. So this is all code for doing that. And it's kind of just implementing the steps I had in those previous slides. So I do want to make a note here that you can use this, at least in R, you can use this TMLE package to help you do TMLE, which I think is, again, better. It's considered a better thing to use than just the G-computation or just inverse probability of treatment weighting. Now, this code is quite simple, right? So it's quite easy to use, but a problem, I guess, is that it won't give you very fine-tuned control over what models you want to fit for your outcome model and treatment model. But other than that, it's pretty good. You can definitely use it. But yeah, sometimes if your data is really, really large, it can be a bit slower, but that's probably not a problem if you just have one data set. Okay, so here's some of the results in the table. It's probably easier to just look at the graph here, which is, yeah, basically I have all of these different techniques that I tried, and the simulation pretty much just shows what I've been talking about. So the G-computation, as long as you're getting the outcome model right, that's pretty good. IPTW, if you're getting your propensity model right, then it's pretty good. For targeted maximum likelihood estimation, you can afford to get either the propensity model, sorry, the outcome model or the propensity model wrong, and you're still going to be okay. But if you get both of those wrong, then it is going to be wrong still. So it's not like invincible. And then these other methods. So when you have the wrong model for your outcome model for the G-computation, then that's not going to work. And then same thing for the IPTW. And then there's also this naive mean, I think is this one. The naive mean. So if you just look at the mean within the treatment group and then subtract that from the mean in the control group, then that's the result of that. So obviously it's not, that's why you can't just do that if you have observational data without an RCT. So that's all very good. And so I guess one thing I didn't talk about that I also won't be talking about is how do you actually do inference when you use these methods. So I didn't really talk about like confidence intervals or anything here. But basically, there's just some results proven in the literature, and you can just use a formula to get the confidence intervals as well. And this package, this TMLE package, will also just output it for you as well. So you can look into that if you're actually interested in using this. Okay, so that was the simulation results, which is pretty much exactly what I expected. Otherwise, I wouldn't be showing this right now. So, but next, I just want to quickly look at what happens if you actually do have an RCT. So what exactly, like from a simulation standpoint, what is an RCT? So like in this previous non-RCT study, I had this probability of assignment, probability of getting treatment being dependent on my severity X. But for an RCT, it would instead look something like this. So here, I just have my probability of assignment, probability of getting treatment being equal to 0.2 for every single person or every single sample in your simulation. And then doing that means that you actually have an RCT. So what happens to my methods if you do an RCT? Well, that's what it looks like. So yeah, an RCT is pretty magical. It lets all your wrong methods just be right. And in particular, you can definitely do this. If you have an RCT, then you can just get away with doing this, taking the means of your groups and then subtracting them, and you're good. Okay, so finally, I want to talk a little bit about validation. So I talked all those, like all those. Oh, I spent how many minutes? Yeah, too many minutes talking about those methods. But you do want to make sure that your outcome model and your treatment model is actually correct. Because if they're not correct, at least to the best of your ability, you want to make sure that they're correct. So if they're not correct, then even targeted maximum likelihood estimation, that's not going to save you. So here I have just three like general points, things that you can pretty much always look at, because for these methods, often you might want to, maybe you're often doing like machine learning, like boosting, whatever, maybe some new hot AI method to do a prediction. Then those all might have different ways of trying to validate whether or not your model is actually correct. So I guess these three things are just some very general things you can pretty much always look at. So for continuous outcomes, you want to have a look at your out of sample prediction. So you want to split your data set into out of sample and in sample, and then see whether or not your well, how your out of sample prediction is going with the outcome model that you might have fit. In particular, you don't really want to see any curvature or anything like that. And then if you have like binary outcomes, and then also for the probability of treatment models, you can look at some out of sample calibration plots, which is just checking that basically it bins your data into several cuts, and then sees whether or not your model is kind of correctly getting the proportions within those cuts. So I won't go into it too much, but those are things you can look at. And then finally, you should probably also check the plot of your propensity scores by the group to check if there's any overlap. So Nick has already kind of talked about this in a seminar. So if you're interested in looking at that, you can check out the seminar. And so finally, I do want to leave you with some conclusions and caveats, in particular caveats. So the methods that I just talked about, they're good for observational data, and in particular when one isn't sure about the form of the outcome model or the treatment model, or both. So if you really don't want to make any of those like linearity and normality assumptions and stuff, and something like the average treatment effect is something you're actually interested in, then you can use these methods. So a caveat here, a lot of non-parametric methods like the machine learning methods, they often do require large amounts of data to do well. So if you have a very small sample size, it's something you want to kind of just be careful about. Don't be too confident in your results. And then, so like for example, even fully parametric, for example, generalized linear models, your estimates can actually still be biased in small samples. So this definitely isn't something you necessarily want to do if your sample size is very small. And finally, just nothing is really a silver bullet for causality, because again, you can always think about those philosophical things that I was talking about in this slide when you're lying in bed tonight. So, yep, thank you. That's all I want to talk about. Yep, any questions?
Yeah.
Yep.
So if you use these methods,
Yep.
can you get standard errors to your?
Yes. So yeah, I didn't talk too much about it in these slides, but the yeah. So the question from Eve was that with these methods, is it easy to get standard errors for my average treatment effect estimate? And the answer is yes. So I didn't like include any formulas for the inference in these slides, but like so I know for a fact. Actually, I haven't actually done it for these two before, but I know for a fact that for the targeted maximum likelihood estimation, which is my recommended kind of method, there's been a lot of like good, solid theoretical work done to actually derive what the standard errors should be, at least asymptotically, and then you can estimate those as well. And it's just the formula, so it's not you can just apply the formula, or you can just use the package and I give it to you, and that's great. Yeah. Yep, there's a question online. Robert, you have a question? Yeah, Robert, you're still muted.
There we go. Can you hear me, Nixon?
Oh.
Can you hear me?
Yeah.
Yeah, thanks, Nixon. That was very interesting. So just a follow-on question, and that is, can you say anything in general about the precision of targeted maximum likelihood compared to G-computation or inverse probability of weighted estimates?
Yep, sure. So this, so I think the question should already be recorded and everything, right? So yeah, the question is, for anyone who didn't hear, maybe in the room, the question is, can I say anything about the precision of targeted maximum likelihood estimation compared to inverse probability of treatment weighting and G-computation? So it's a great question. I think the theory says that asymptotically, it's usually, at least asymptotically, it's always going to be at least as good as either the better of the inverse probability of treatment weighting or the G-computation. And in particular, I think if you have both the outcome and the treatment model correct, then with a large enough sample size, it's actually guaranteed to be asymptotically efficient. So I think it's like basically it's at least with a large enough sample size, it will always be better than the G-computation and the inverse probability of treatment weighting. Although with smaller sample sizes, they might actually end up being similar. Yeah, but it shouldn't ever really be much worse.